So here's a shortcut for electron configurations. You might like this. Now, we've mentioned that the electrons are really important when it comes to bonding and chemical reactions. And so we really want to have a map of where all the electrons can be found so that I know whether this atom is compatible with another atom. Will their electron clouds likely interact with one another? Now, here they're talking about sulfur, the electron configuration of sulfur. And they give it to us down in the bottom here. Sulfur, the full electron configuration of sulfur. Now, should we just double check and make sure that's right? There's two ways we could check to see if that's right. We could count the superscripts, because the superscripts represent the number of electrons in that orbital. So I've got, let's see if I can do this. I'll try to make it really skinny. There's 2 electrons, plus 2 more for 4, plus 6 is 10, 11, 12, 12 and 4 is 16. Is sulfur element 16? Why, yes it is. Of course it is. Now the other way we could double check and make sure this is right is that we could just look at the very last orbital, 3p4, and we could go back to our periodic table. I'm looking at the one in the back of the book, and we could say, oh, what element would end 3p4? All right, so I'm in the p block. The 3p, fourth element in, 1, 2, 3, 4. Yes, it's sulfur. Aha, they got it right. Okay, so the electron configuration is that like kind of shorthand way of showing the orbital diagram. Here's kind of an orbital diagram, and I like this, that we would have 2 electrons in the 1s orbital. They would be electrons in a spherical region really close to the nucleus. Then we'd be a little bit farther out in the 2s and the 2p. Now obviously they're not showing all the shapes, but they're showing that they'd be electrons that are a little bit farther from the nucleus. The 2s is filled with 2 electrons, and the 2p orbitals, there are 3 of them, and they would all be full. Then we would move out to the 3rd energy level, and we'd have the 3s with 2, and the 3p. Now I kind of like this. Do you notice that what's going on like right in here? The 3p would have 4, but we fill them 1 electron at a time before pairing. So with 4 electrons and 3 orbitals, somebody's got to get paired. It's fine. Okay, so we've got 2 little vocab terms to mention then. The first is core electrons. Core electrons are all the inner electrons. The valence electrons are the electrons in the outermost energy level. Now, all electrons are important. They're all very important. But when you really think about it, let's say this atom, this model of the atom down here, this atom wants to interact with another atom. Well, yes, it's the electron clouds that are going to overlap and either share electrons or transfer electrons and somehow interact with one another. It's the electron clouds. But most specifically, what part of the electron cloud are we most concerned with? The outermost electrons, the valence electrons. Of all the electrons, are the most important. They're the first ones that are going to interact with electrons from another atom. It's always going to be the electrons on the outside, the outermost electrons. The core electrons are cool, but they're all electrons that are closely held to the nucleus. And by the way, since the nucleus is, whoopsies, last time I checked, positive, the nucleus is positive, and so all these negative electrons that are in the orbitals close to the nucleus, they're very attracted to the nucleus. So the core electrons are really stable. They're in full orbitals, that's a good thing, and they're held really tight to the positive core, the positive nucleus. But it's the valence electrons that could get themselves into a little bit of a bind. They're kind of far away from the nucleus. They're maybe not held as tightly to the positive nucleus, and they're the first ones to interact with other atoms. So we're most concerned with the valence electron structure, which then brings us to this shortcut. It's a noble gas shortcut. So the noble gases are the group all the way on the right-hand side. Helium, neon, argon, krypton, xenon, radon, and the newest noble gas, number 118, oganesson. These are your noble gases. What's interesting about the noble gases is that they have all of their orbitals full. Any orbital that's occupied by electrons in a noble gas is a full orbital. All of their S's have 2, their P's have 6, their D's have 10, which is one of the reasons why the noble gases are known to be pretty stable and non-reactive. They've got nice full orbitals, which is very stable. And so here's what we can do. We can do a little shortcut and really only focus our electron configuration on the valence electrons. So on a periodic table, you do this. I'll go back to that sulfur. These are my noble gases. You go backwards to the previous noble gas. So if sulfur is number 116, I have to go backwards to number 10, neon. But then you can write the symbol for neon in brackets, and it shortens it up by 10 electrons. All of the electrons in neon are full, nice full orbitals. They're really stable. They're close to the nucleus. So you can just start with comes after neon. So it puts you in the right row. Oh. So if it puts me in the right row, I'm already at 3s2. Oh, sweet. 3p4. And guess what we're really focusing on then? These guys are your valence electrons. You're really showing the valence electrons. The 10 electrons that would be shortened up here, these are your 10 core electrons. And so it still has 16 electrons because putting neon down represents 10. And then you've still got 2 in the S and 4 in the P. But we're really focusing on the valence electrons. Those are the ones that are going to be involved in any kind of a chemical reaction or a bond. And so that's what they're trying to show here, is that we can shorten up this first set of orbitals and just say neon. And then all you're showing are the electrons in the highest energy level. So the electrons in the highest energy level are all the electrons in the third energy level. The third energy level is the highest occupied by electrons in sulfur. So any electrons in lower energy levels are called core. I'm going to shorten that up with neon. And then I write all the valence electrons in the outer orbitals. Now, valence electrons means outer energy level or outer energy shell. And so it's not just the outer orbital. We include all electrons in the third energy level. So it's the 3s for 2 and the 4p for 4. Or the 3p for 4. Hello. All right, let's try strontium. Let's do strontium with that noble gas shortcut. So I'm going to go back to my periodic table and find strontium 38. There he is, strontium number 38. Okay, so 38 electrons, that's kind of a lot. Now obviously if it's something like, I don't know, carbon, I'm probably just going to write it out. I mean, the shortcut doesn't make it that much shorter. But when I've got 38 electrons, yeah, I'm going for the shortcut. You have to go backwards to the previous noble gas. So this is 38. I need to go backwards. The closest will be krypton. That's not bad, 36. So for strontium, I can go brackets, krypton. By putting krypton in brackets, this saves me 36 electrons. Yes! Now that's a nice shortcut. I like that. And then what it does is let you start in the right row of your element. So after 36 krypton, I'm already at 37 and 38. all I have to write is 5s2, done. There's strontium. By putting krypton in brackets, that saves me 36 electrons. And then I just have the outermost valence electrons. They would be the 2 electrons in the 5s orbital. Think about how sweet this would be for osmium. Remember in the last section we did the electron configuration for osmium, and it went all the way across your page? Yeah, watch this. Osmium. I would go backwards to the previous noble gas, which backwards would bring me to xenon. That's okay. So I could go xenon in brackets, and then I just write whatever comes after xenon. That saves me 54 electrons. So I'd already be starting with the 6s for 2. That would be cesium and barium. Then I gotta go back down and pick up lanthanum, so I'd be in the 4f for 14. Lanthanum, number 57, all the way across to ytterbium, number 70. But then I'm like almost done. Then number 71 is back up into the 5d, and osmium was 1, 2, 3, 4, 5, 6. Isn't that nice? Now technically the valence electron is the outermost electron, which in this case the outermost electron is technically the 6s2. Those are the ones farthest from the nucleus. But sometimes we might still have a couple other orbitals that are showing, even though it's technically this shortcut. Well, it's still a shortcut. It saved me 54 electrons. And it's really showing the most important electrons, the ones that are going to be on the outermost edge of the electron cloud. For more shorter atoms, like the strontium and the sulfur, you'll really just get the electrons in the outermost shell, the most important valence electrons.